Hello, everyone. Welcome back to this next session. We are happy to welcome you and hear some really interesting presentations. My name is Doris Klein. I'm from DLR, the German Aerospace Center. And this is my co-chair.
Hello. Good morning. My name is Gemma Maza. I'm from the European Union Satellite Center, and we are very happy to welcome you here in the last session that we have of this marvelous conference. So I would like just to mention a little bit about what you are going to see today. So the session is related to societal applications that are related to risk, resilience, and resource monitoring. In this session, we will explore how the Earth observation and geospatial analytics are being applied to some of the most pressing societal challenges that we have nowadays. So we will see from urban resilience or wildfire management to climate adaptation and environment monitoring. Our speakers today will present a diverse of set applications, ranging from deep learning, wildfire mapping, to very innovative platforms. So will be, I think, very interesting for all of us. I don't want to be so long, so only to see that we have some changes. So one of our presenters will not be here, so maybe we will have more time for the other presenters to be more relaxed, so if you have more time for questions and answers.
Sorry, I have just to add, please still stick to the time because we started 15 minutes later. So we please come to the stage. Our second presenter, Anita Splano from Planetec.
Yes, thank you for the opportunity and the presentation. I'm Anita Splano. I work in Planetec Italia like a technical specialist in Reticus team. And today I'm going to present a new multi-risk platform developed by Planetec Italia called Reticus SafeLand. Land instability and wildfires pose a serious risk to human safety and environments and infrastructures. Their frequency are increasing also to the climate change and the human activities, with the landslide and mudslides causing extensive damage and loss of life. To meet this challenge, Planetec Italia develops Reticus SafeLand, a service that employs HPC, big data, and 3D digital twin model to monitor territory susceptible to landslide and fires. This service offers a dynamic overview of the territory, enabling the identification of a critical zone and supporting multi-risk mitigation strategies. As I said, Planetec Italia developed Reticus SafeLand under the National Recovery and Resilience Plan within the AI Land Initiative for the Environment Natural Disaster, project by the National Center for HPC, Big Data and Quantum Computing, funded by the EU Next Generation. The 3D digital twin model is developed by Sfera Informatica, and all the geoanalytical indicators generated by the platform are integrated in 3D environments, constituting a 3D digital twin model of the territory. This is a preview of the platform. As you can see, the territory is divided in hexagonal cells. These cells are classified by an automatic procedure based on the access displacement trends and anomalies patterns. Each cell is assigned a level of attention calculated by an inspection priority score that is used to rank inspection urgency and is a values normalized between 0 and 1. The data input for the calculation of this inspection priority score are geospatial data sources and amplification factors. Now I explain one by one all the data input for the calculation of the inspection priority score. The first, geospatial data, are spatial anomalies in stable area identified by the analysis of the mean displacement velocity of permanent scatter and distributed scatter measured along the line of sites and extracted in this context from the EGMS portal. For each acquisition, PS and DS with the same kinematic behavior are grouped into clusters, represented by an enclosing polygon, with some information useful to assign a level of attention and a weight for each cluster. The second are spatial temporal anomalies, identified by the analysis of displacement time series of PS and DS measured along the line of sites and extracted from EGMS portal. The first steps involves to detect a displacement anomalies detecting by a breakpoints that appear in the most recent period of the time series. These breakpoints represent either changes in the displacement velocity, easy identifiable in the time series. Also for each acquisition, the PS and DS with the same kinematic behavior are grouped into clusters, represented by an enclosing polygon, that assign a level of attention for each cluster. The third geospatial data are isolated PS and DS that don't contribute to the generate cluster and so spatial and spatial temporal anomalies. And for each PS and DS, we study the displacement trend time series. In addition to geospatial data, for the calculation, like data input for the calculation of inspection priority score, we have also landslide hazard, hydraulic hazard, and the burn area. Each amplification factor is weighted according to the percentage of the layer in the hexagon with its relevant level of risk. The final weight is a combination between the weight of the geospatial data and the weight of amplification factors. This combination is thought thanks a model called order rate weighted averaging, HOA, that assign weights to different information layers based on their relevance in determining the level of attention of each cell. The data output is values normalized between 0 and 1. And for values close to 0, we have a low attention. So we have a red, we have a green cell, stable cell, and no intervention is needed. For values between 0 and 1, we have a moderate attention, so we have a potential instability in that part of the territory, and is advised monitoring. For values close to 1, we have a high attention, so we have a high risk, and is required an inspection. Each cell is also queryable and provides information like the ID of the cell, the geographical coordinates, so also the information about the municipality and province of the cell, the values of the inspection priority score that assign a color for each cell with its mean velocity, ascending and descending, and the number of PS and DS into the cell, and the maximum area of spatial anomaly and spatial temporal anomalies that I said before. We have also information for each cell about the altitude and the class of slope, the lithology type, the type of land cover and the presence of land cover change, the presence and the area of burn area, and the value of a maximum hydraulic and landslide hazard, and also the presence of strategic buildings and the type of infrastructures. In the end, we have also information about the climate data, in particular to temperature, speed, and precipitation. The service allows end user to obtain more information in detail with some information layer that can be turned on or off according to the analysis that the user wants to do. In particular, we have the thematization of the cell through EPS, the layer about the cluster of spatial anomalies and the spatial temporal anomalies, and all PS and DS that don't contribute to generate the cluster of spatial and spatial temporal anomalies. The layer about strategic asset, so we have a widget with a different type that I can put on or off according to the study that I do, and the type of infrastructure. Lithological mapping with all the class of the lithological mapping. We have also the layer of the files I don't know, this is an example. I set in a preview of the platform, I set only the cell with the files. So in the platform, I see only the hexagon with a files, but it's possible also to set that I want to see the files in 2021 and 2022, and the platform shows me only the files in that year. The layer of landslide by HIFI, and the layer of landslide and hydraulic hazard, and the land cover and the land cover change. So in the end, all this geoanalytical information that we have generated and we show in the platform are integrated in a 3D digital twin model of the territory that supporting predictive analysis and risk management strategies in complex scenarios. The advanced 3D interface fuses geospatial, environmental, and topographical data to monitor and forecast hydrogeomorphological and fire-related phenomena. In conclusion, this platform allows the end user to obtain in detail information to support regulators and decision makers with the contribute of this inspection priority score algorithm that helps detect the critical zone early and support smart prioritization. So the 3D in the digital twin model support the visualization of the platform and offers a comprehensive view of both current and future risk conditions. This approach enables proactive planning, efficient resource allocation, and multi-risk management. Thank you for the presentation.
Thanks a lot for this beautiful presentation. Are there any questions from the audience? If not yet, I would like to start with one. So you showed us a really comprehensive platform with a lot of information for decision making. So I was wondering, could you tell us something about, did you already test it with the users? So do you know how good it is adapted and how easy it is for them to extract then the information they need in the end?
Yes, this platform is adapted to the end user. So the end user, if want to see more information or in-detail information according to their analysis, can ask different layer to input in the platform.
If no other questions are, thanks a lot.
Thank you.
And we move on to the next speaker.
Now we give the floor to Ioannis Kotaridis. He will present in burn area detection in Greece and how the deep learning and using Sentinel-2 data, it could be very useful for this purpose. Thank you.
Thank you, Gemma. Well, hello everybody. This presentation is about a use case related to burnt area detection in Greece, where we leverage deep learning and Sentinel-2 data. So I'm going to explain the motivation behind this research, the data and the methods used, and also see a few key results and insights. So what's the challenge? You may know that in Greece we face it's a major challenge. They are becoming more severe and increasing in numbers, so they are driven by climatic changes and also driven by human activities. So there is this constant need of precise and updated maps of burned areas for wildfire management. We know that the ground surveys are costly and time-intensive, so here comes satellite remote sensing that offers a really valuable solution to monitor large and often inaccessible landscapes. So, why Sentinel-2 data for fire detection? First of all, the spatial resolution of 10 meters is more than enough for this type of analysis. The revisit time of 5 days provides really, it may not be the most suitable for rapid response measures, but offers really valuable information to monitor the impacts of the fire and post-fire assessment. And finally, the MSI sensor of Sentinel-2 data enables the detection of really subtle spectral changes in burnt vegetation. So on the right side, you can see a few examples of burnt areas, the burnt scars, as they can be seen from a Sentinel-2 image in a false coron composite of SWIR, NIR, and red bands. So, burned area for sure is a critical task in remote sensing. Traditional methods such as the burned area index, normalized burn ratio, and traditional methods such as machine learning techniques have been used a lot to map the burned areas, but may show some limitations in more diverse landscapes. So here comes deep learning and its models that offers really valuable solution for semantic segmentation tasks. And in specific, the unit architecture and its encoder-decoder structure allows to integrate contextual information for multiple scales that this is quite important for remote sensing applications. A few things about the study area. It's covering the mainland, but also the islands of Greece. We have a diverse topography, coastal regions, mountainous terrains, and all of this contributes to an increased spectral diversity. So, 20 Sentinel-2 Level 2A imagery have been used from the years 2023 and 2024 that cover the fire events cataloged by the Copernicus Emergency Management Service. These images were selected based on limited to no cloud coverage, especially over the burnt areas. So, we have a dataset with 21 wildfire events across Greece from the past 2 years that cover a wide range of wildfire incidents, ranging from really small ones to massive ones, such as the one that happened in East Macedonia that burned nearly 94,000 hectares of land. Now, the methodological framework for this study involves a few key steps. First of all, we have the data preprocessing, where the Sentinel-2 imagery are resampled and stacked using only the SWIR, NIR, and red bands. Then we perform binary classification to burned and not burned areas, when it was ensured that representative samples from across the scenes are selected to capture the spectral variability. And from these classified images, we generate the training data in 64 by 64 tiles to feed the deep learning models and train them. So we have the training and validation of the deep learning models. In total, 8,534 training samples were used, and in specific, the unit model depicted the highest accuracy of 96% with 0.95 F1 score. In the table below, we can also see the performance and the metrics of a few other models, and also the training time, that's really important, that ranges from 24 minutes to almost 2 hours. And after the training and the validation, we have the testing of the model. In specific, the unit was selected to be tested on 2 wildfire events with codes 747 and 767, and an overlap analysis was performed. So, with the first one, the unit model had a 94.5 overlap, and with the second one, 95.7 overlap, demonstrating also really high accuracy. And also in the table, we can see the areas calculated by the unit model in comparison with the EMS reference data, and we can notice that the values are really close. But it's also nice to visualize this comparison. On the left, we can see the comparison between the EMS product 747 and the unit model with a red color, and on the right, the same comparison for the EMS 767 and the unit model output. What I would like you to keep from this slide is that the model can capture even the finest detail, as it can be seen from the insets below. And keep also in mind that there may be a small difference in the timing of these two products, because the EMS service use also very high resolution data. So yeah, that's the reason. Now, I would like to highlight a few key advantages of this framework. First of all, it's not only the high accuracy of the unit model, but also the fast training times. Of course, it's tailored to work nationwide in Greece at this specific use case, but it has the potential to be extended in other Mediterranean regions that face similar wildfire challenges, in order to offer the public authorities and the stakeholders really valuable information to coordinate emergency response and also plan long-term recovery initiatives. I would also like to give some future directions. First of all, there's the potential to further enhance the deep learning model by integrating additional data sets and also make it more robust across different conditions, in a sense that it can be used in a broader scale. As I said before, it's also nice to test its applicability in other regions, such as Italy, Spain, and Portugal, maybe. And a last thing is the idea to support operationally. It can be deployed and integrated into an existing emergency management system. Of course, the infrastructure in this case will be hosted in the cloud, and it will be offering continuous monitoring capabilities with regular updates. In practice, there is this idea of integrating the model into a pipeline where, as soon as a Sentinel-2 imagery is acquired, it can be obtained and ingested through an API, and the already trained model in a few minutes can produce a burn area map, and it can be transferred directly to the public authorities and the stakeholders of interest, for example, with via web dashboard. Yeah. So, thank you for your attention, and that's it.
Thank you very much. There is any question? Yeah.
Just a question. Are you in touch with the people in the JRC, I believe, who run the Copernicus Emergency Service, whether they would be able to include it there? I mean, that would be the best.
Could be. It would be. In fact, I had the opportunity when I was working in the industry to work in the Copernicus Emergency Management Service. I was produced these products, and I know that they are done like with unsupervised or manually the techniques. So I think it would be really nice to ingest such type of framework in a Copernicus as a Copernicus service. Yeah, that's really nice, I think. Yep. Thank you.
Thank you very much. Thank you. Close.
So we move on to our next speaker, which is Andrea Sibilia from JRC. And he will talk about space-driven geospatial analytics for pan-European human settlement. It's fixed asset valuation. So please, the floor is yours.
So good morning, everyone. My name is Andrea Sibilia. I work for JRC as an external consultant. And I work in the project called Risk Data Hub. I'm going to present this work that we did together with our GHSI colleagues. So during those days here at the conference, we heard a lot about the baseline information that we have. We have plenty of baseline information available. However, this information is scattered across multiple layers, multiple data sources. So there is the need to leverage Earth observation data in order to create actual layers that can be used by decision makers, and they can also help them to smooth the policy decision-making process for adaptation, basically. In this case, in this study, we focus, for example, on the monetary value of human settlements, because it's a critical aspect that is lacking of harmonization across Europe. And the idea is to combine basically the monetary value with the built-up in order to get the value of tangible assets like total built-up, residential content, and infrastructure. And eventually, we also want to combine this information with an hazard footprint, the river flood in this case, at a 100-year return period. And actually, the analysis is for the whole Europe. North of Italy, it was a very, very early stage of the project. So the objective is to create a scalable geospatial workflow to combine the monetary value of fixed asset with the total built-up, and then combine again with a hazard footprint, and eventually the output that we get is going to be integrated in a disaster risk management information system and make it available to the public. In this case, the management system is the Risk Data Hub. How we do that? We took two different layers, basically, as baseline information. The first one is HANSE, Historical Analysis of Natural Hazard. The project started with creating a database, an impact database of flood events across Europe, but they further expanding the number of hazards that they are creating. And within the project, they released also this exposure model for multiple epochs. And this model is a grid of 100-meter resolution at 100-meter resolution. And they provide also the monetary value for fixed asset and also for additional sectors. They did that combining the information of the GDP at NUTS3 areas. If you're not familiar about NUTS areas, I'm going to explain in a minute how they are. And also the land use data from Copernicus, so the core inland cover. The second main data set that we use is the global human settlement layer. We heard a lot about it during this conference. And well, they have several products, of course, across time. The data comes from Landsat Sentinel data, Sentinel-2 data. And we use, in this case, for the analysis, the built-up surface at 100-meter resolution. And the good thing is that we didn't have to do much resampling between the two layers because they had exactly the same alignment. So HANSE developed their data using the same grid that it was here on the global human settlement layer. So the whole process that we did was a huge iterative process. So we went through the times, through all the years that we had to overlap the two layers that we have. And we have a new layers with the GHSL data combined with the monetary value, so the monetary value attached. And then the newly created layer was overlapped again with GISCO NUTS3 areas. So for the ones who are not familiar with that, the European Commission provides those standard classification administrative units, and those units comes from the country level up to the subnational level. NUTS3 areas are pretty much provinces, and it's the level right above the municipalities, basically. So we combine with administrative units. We got also the degree of urbanization from GHSL to get information for rural areas, urban centers, urban clusters, and city center, and then also the overlap with the hazard footprint for river flood at a 100-year return period. We did several zonal statistics to get the data by asset, by degree of urbanization for several years. I give a very wide overview of the results that we got. So in terms of total monetary value that we got was that in Europe there are about 92 trillion euros of total monetary value of asset. And most of the value is, of course, concentrated in urban clusters and city centers. The 75% of the value is in this kind, in these urbanization typologies. And this percentage is constant over time, so it doesn't change much from 2000, at least, the first year that we got in the analysis. What we also notice is that urban centers and urban clusters and city centers also increase their monetary value faster compared to rural areas. And actually, the urban clusters expanded a little more faster than the city center. If we look at it spatially, we can see basically that there is a sort of east-west gradient where eastern countries have a lower monetary value, a lower total monetary value in terms of absolute values. Here in this case, the first map with red shades is total residential built-up in terms of monetary value. The blue shade is the percentage value within the percentage value compared to the total within Europe, and the small map is the degree of urbanization from GHSL. As you see, it's basically almost everything is green, so the monetary value is actually concentrated in very small areas, so big urban centers. But what happens when we also introduce the river flood? Well, this picture changed completely, so we see that there is no more gradient east-west. Actually, eastern countries we see that are more red in this case, because this is the percentage of exposed value that we got for each NUTS-3 area, and we see that the picture totally changed in this case. So that's the importance of combining. It's a simple example that shows you how combining data, so that data set we are able to get additional insight, and a map like this can help also policymakers and decision makers to target better their policy in order to protect areas that actually need to be protected. As I said at the beginning, those results are going to be integrated in the Risk Data Hub. So we already have a data visualization application, a beta version, with the results of this analysis. If you scan the QR code, you can see it also on the mobile. This will be fully integrated within a exposure section that we have on the Risk Data Hub. Here we have a section dedicated to vulnerability, risk, exposure is going to come, and also a database of loss events from the past. It's not finished, let's say, because we also aim to further develop our analysis in order to extend the number of hazards, fully integrate the results that we get into our risk analysis process, and also combine this information with additional data that comes from basically space. So hazard footprints, like the Myriad project that provide this kind of information, but also Copernicus, our colleague from Copernicus in JRC that are providing this kind of information. So I thank you very much for your attention.
Thanks a lot. Are there any questions from the audience? Please.
Thank you so much for the presentation. It was really interesting. My question is related to the collaborations you've had. In Europe, as far as I know, the European agency EIOPA is the one responsible to regulating the insurance sector. Have you collaborated with them in this respect?
Yes, we have an informal agreement, let's say, nothing involved in terms of financial and so on, but we have a collaboration because, especially on the lost data, in the database that we developed, we created a method to create a unique identifier to identify events. And EIOPA is really interested in that because if we are able to provide this identifier to them, they can provide again to the insurance company, and insurance company can provide data about insurance losses against this identifier. So this will help the streamline of sharing data with the insurance companies. So we have collaboration with them, yeah.
Any other question from the audience? If not, may I just ask one question? Because we heard this morning in the panel from the policy side that one really important issue is the data quality and trustworthiness. So I was wondering, how do you validate the data, and did you get any feedback from the insurance companies, for example, or from other users on the data sets?
It depends by the data that we collect, because in the Risk Data Hub, well, the aim of the project is to collect data that are already produced. So we usually do not create the data on our own, because it's already a huge task just to collect and harmonize data that comes from different platforms and so on. So data that we collect are usually already validated. So for example, the river flood comes, in this case, comes from EFAS, from our colleague from the FLOB team. The baseline information that we use about human settlement were from GHSL. The other layer that we use, the Hanze one, in that case was already published on a high-level scientific paper. So it already went through a validation process. What we do, for example, when we collect lost data, we do a bit of data processing, but it's mainly to allocate the losses in the areas that are actually impacted. The idea is, eventually in the process that we have, we want to be sure that when you aggregate the data again, everything, all the numbers are correct. So if you recorded 300 fatalities across 3 different areas, we are able to disaggregate this information using additional data like exposure. So we say, okay, the exposure in this area is like this. So when you reaggregate back the data, you end up with 300 fatalities, not more or less. So we do not lose any information in that case.
Thank you.
Okay, now we move to the next one. So we welcome to Selma Dissing, that she will be presenting now artisanal and small-scale gold mining detection in the Amazon forest using contextual data. So, thank you, Selma.
Okay. Hello, everyone. My name is Selma, and today I will present to you my thesis that I conducted as part of my master's in information studies at the University of Amsterdam. This was supervised by Jan Christoph Gallo, and the title of my thesis is Artisanal and Small-Scale Gold Mine Detection in the Amazon Forest Using Contextual Data. So, artisanal and small-scale gold mining, or ASGM for short, is a major driver of deforestation and land degradation in the Amazon. Unlike traditional industrial mining, it is quite informal and mobile, which makes it very hard to monitor. And traditional field inspections are quite slow and expensive. And since then, remote sensing has become a key tool for monitoring ASGM. But current approaches rely predominantly on optical spectral information. And this kind of creates some challenges in distinguishing ASGM activity from spectrally similar land use changes, such as bare soil, dry riverbeds, and agricultural clearings. And this limitation kind of shows to us that optical satellite imagery on its own is not enough for reliably detecting ASGM activity. So one way to overcome this challenge is to turn to contextual data in many domains, for example, in both product recognition and medical imaging. Adding contextual information has already been proved to improve classification, where the surroundings of an object kind of provide some crucial clues. And in remote sensing, contextual features such as proximity to infrastructure has also already been proved to improve classification. And in this research, we turned to OpenStreetMap, or OSM for short, which is a widely used crowdsourced data set with layers such like transportation networks and infrastructure. And because mines follow some certain spatial patterns, such as being always near water, being quite remote, and dependent on road access, this contextual information may help the model distinguish ASGM sites from spectrally similar areas. So our research asked, to what extent does integrating contextual geospatial data enhance the performance and interpretability of an ASGM detection model using satellite imagery? Specifically, we tested whether combining Sentinel-2 imagery with OpenStreetMap can help distinguish ASGM sites from these other visually similar land disturbances. And this work builds upon the open source detection pipeline developed by the Earth Genome Project, Their baseline is a lightweight CNN trained on only Sentinel-2 patches, able to detect ASGM activity. And we kept the same architecture, but we extended the input with additional OSM channels, allowing the model to learn both spectral and contextual patterns. A bit about the study. We focused on the Bolivar state in Venezuela, a region in the Amazon which has very dense rainforest and extensive ASGM activity. For ground truth, we used Earth genome sampling points, which included both confirmed mining and non-mining locations. And from these points, we extracted Sentinel-2 image patches using Google Earth Engine at 2 different scales so that we could compare. We took at 48 times 48 pixels and 256 times 256 pixels. And because the data set was very imbalanced, we tested both with and without class weighting. Then to add context, we extracted 5 different OSM feature types: the waterways, highways, land use, buildings, and airways, and converted them into separate raster channels. We also compared 2 types of negatives: curated samples from Earth genome, and then we also sampled ourselves random points across the region to test more model robustness and more ambiguous and less curated examples. So in total, we did 10 different experiments varying the 4 different factors: patch size, different negatives, the class weighting, and the OSM integration. So overall, the results show 3 clear patterns. First, that patch size matters. The larger patches consistently outperform the smaller ones, likely because they capture more of the surrounding areas, which is critical for determining ASGM activity. Secondly, negative sampling was also critical. The curated negatives produce stable results, while the random negatives produce very variable results, but they also do better reflect real-world situations. And in fact, the strongest spectral-only model came from random negatives, which kind of indicates to us that the model benefits from seeing more realistic examples. And then the third one is class weighting and how it interacts with OSM. So in the curated settings, class weighting actually reduced precision and increased false positives. But with random negatives, class weighting on its own led to very poor results. But when adding OSM, it stabilized training and the model performed a lot better. So the key takeaway here is that OSM is not a universal improvement. Its effectiveness heavily depends on the patch size, the sampling strategy, and the overall training setup. And then to better understand how the models behave, we compare the errors between the Sentinel-only model and the OSM enhanced model. So here on the left, we have the Sentinel-2 only model, and we can see that all errors are false positive errors, which means that bare soil was misclassified as mining. And then when we look at the OSM enhanced model, we can see that many of those false positives disappear, but the trade-off is that some false negatives occur, which means it misses sometimes mining sites. So the takeaway here is that OSM does reduce false positives and makes predictions more precise, but it also makes the model more conservative, occasionally missing difficult mining sites. Then to better understand how the model makes decisions, we used GradCam visualizations to show which regions in the input that most influence the prediction. And here, if we look at the second to last image for the baseline model, so the Sentinel-2 only model, we can see that the attention is drawn to the bright, clear areas, which makes sense because it is using spectral data only. And then when we look at the OSM enhanced model, we can see that its attention shifts more towards some meaningful structures like the waterways here from the OSM data. So the takeaway is that OSM guides the model toward more context-aware and interpretable predictions. Then to understand a bit which OSM layers contribute the most, we ran an ablation study removing one feature type at a time. And when we removed highways, the performance dropped sharply to 0.59, which tells us that road networks are a single most important contextual feature, whereas the other layers just had a more moderate effect. So here the takeaway, OSM layers do all help the model, but roads provide the strongest contextual signal. So to bring it all together, OSM helps make ASGM detection more precise and interpretable, mainly by reducing false positives and guiding the model toward more interpretable and meaningful structures. But it's not a universal fix. Its impact depends on the training setup and the quality of the contextual data. And then the trade-off is that while precision improves, the model can sometimes become more conservative and miss subtle cases. And among the OSM features, roads clearly stand out as the most influential signal. So with that in mind, the key message that I want you to take from the presentation is that combining Sentinel-2 imagery with some type of contextual data, like OSM in this case, is a promising path toward more accurate and reliable detection of ASGM, and a direction I think is worth exploring further in research. If you'd like to check out the code or any of the experiments, the GitHub repository is linked here. And if you have any questions later, please feel free to reach out to me or my supervisor. Thank you very much for your attention, and I'm happy to take your questions.
Are there any questions from the floor? No? Okay. In that case, I have one for you. I think this is a very interesting topic, the one that you try to investigate. It's not easy at all, because as far as we know, this identification of clear areas in the middle of the forest could be many things. We know that it can be even, as you mentioned, bird foil, forest cleaning. So I see that you try to use open data or open source information that is very useful, but then you use like any classification for the Sentinel. I mean, because finally for the gold mining, they are using not only water, but many other materials. So did you consider to make this classification with the spectral values of the image, try to differentiate, to make the difference between the gold mining and other open areas?
Sorry, do you mind repeating that one more time?
Okay. So not only the use of other information, but make a classification of the Sentinel-2, trying to distinguish with the normal bare soil, with the bare soil that maybe could have a different response inside the remote sensing values.
Yeah, no, I think that would be super interesting to look into. I didn't do that, no. Yeah, I think I was a bit limited to finding the sampling points. It was very hard because obviously it's not very open source data, which mines are illegal or legal. So I found this open source project which had a bit of everything. So I think I stayed within their scope and only used their points. But I think that would definitely be interesting to look into.
Any other questions? No? So maybe we give the floor to the last one.
Yeah, thank you. So we come now to our last speaker. That's Pedro Concalves from Terra2. And we return to the topic of fire. So although we stay in Latin America and the Caribbean, and we will hear more about the automated Earth observation chain for wildfire management.
Thank you very much. So I'm your last presentation of the day and of the conference. I'm replacing Mauro Arcoracci, that was the main author of this paper. This is a big team from Terra2 and also IndraSpace in Spain. We are focusing on taking algorithms, Earth observation algorithms, to wildfire management in an operational center in a continental scale. So I will first introduce you a little bit what is the Copernicus LAC, what are the EO services, what type of development and demonstration, and really the involvement with the users. So this is a bottom-up approach, that understanding from the users what are the needs that they have there. First of all, the Copernicus LAC, it's a regional project. The objective of the European Union and ESA is the establishment of a regional center covering Latin America and Caribbean, installed in Panama. Its goal is really to co-design with local institutions Earth observation services that cover mainly for the prevention and recovery before disasters, and also capacity development, local capacity development. This is an agreement between DG IMTA, ESA is an implementation partner, as a steering committee with the Panamanian government, EU, and delegations of DG ECHO and GRC here. Mainly, we are focusing in two projects here. From one side, there is the Copernicus-like platform. So we are developing the open source tools to deploy a platform in Panama with the necessary tools in terms of processing, data discovery, analysis, analytics, and this is managed by TerraDue. We are with T-Systems on this one, and University of Chile. And then there is another project covering geoservices that is managed by Indra Spatio in Spain. And here the idea is discovering and co-designing services in 4 main areas: hydrometeorological, wildfires, geological hazards, exposure. All of these, you have more information in these links. And in this presentation, I will focus on what are the first services that we are deploying. So we are hosting 8 open source services covering wildfire events. Not only the detection of wildfire, but also danger and vegetation recovery. So indexes focusing on fire risk danger, but also the recovery. And this is 2 main types of services that we at TerraDue are very used to. This type of scenarios is having the same algorithms, the same software being deployed in different types of operations. So from one side, you might have a few services for specific use cases are done systematically, and then you have the same services or other adaptations of the same packaging of application that are more used on demand. So here we have a set of services like burn area mapping, fire danger, fire recovery, burn area severity, and so on. And this you can then play with these services in terms of orchestration also. You have a systematic, you have detected a fire. If the fire is no longer detected, let's start a recovery processing chain and analytics. And so what we have is different workspaces target for different users, different communities. So in the back office is processing stuff, but then you have different facets, different views, depending on which is the community that's observing that data. For example, we have a wildfire result explorer that is really doing the systematic, that is a way of seeing the systematic processing chains. So it's something that is making the layers in terms of fire danger, hotspots and burn area, post-fire vegetation recovery, and it's a way of the user to observe and to see those inputs. The first one, burn area mapping, is really detecting the active fires using Sentinel-2. I will show you in the next slide. This is an evolution of the ESA CCI algorithm. So part of the team that was developing, and even our colleagues of Brockman was developing that algorithm. Part of the team now is also in Indra, and they're evolving it, and is more taking something scientific and saying, okay, how do we put this in operations? How do we put this in a near real-time environment? How do we take consideration also of cost in terms of what is the operational cost? Then we have it here. And in fact, there are a few changes that they did in the original algorithm, like the pre-fire event is now a time series kind of calculations they are doing. There are stuff that was evolved, but it's basically using Sentinel-3, Sentinel-2, VIRS data, and trying to detect the burn area mapping and putting this information to the user. All the service specifications, tutorials to use the service are online. So the idea here is also we are co-designing with the community locally. So most of the stuff now is already is in English and in Spanish. We have to be also in Portuguese. But we are co-designing with them, and is a way of sharing that information and that deployment. From TerraDue side, what's happening here is that we know how to package algorithms, we know how to put this into systematic processing chains, and now we can do a processing environment that then allows the user to have a view, a different facet. So you might have a facet that is very digital twin kind of thing, 3D, you can do it, but you can go for a technical one. You have different dashboards that you can do analytics of that data. This one. Then we are testing in sense of this is Los Angeles in Chile, not in the US. There was a big fire in 23, so we are now analyzing past events and checking how this reacts in terms of a near real-time area evaluation. Also here in Chile, the different fires. And then another type of thing is fire danger mapping. So you have algorithms systematically running our data sets in the sense of, okay, what is a given region, what are the fire danger, and then defining stuff like low, minimum, moderate, defining this type of classification that is based with several other informations like fire weather and grease data that is designed also with the local institutions. And you have also here, again, the service specifications, the tutorials, how to use it, the software, and so on. This one is very interesting. It's post-fire vegetation recovery. So it's also from a point of view of platform is interesting in the sense that you are detecting the fire, but then the platform itself has a memory and saying, okay, this fire is no longer detected. So let's now start a new event. Let's now start a new analysis. Let's see how this vegetation evolves. And then it becomes an action of evolving the vegetation recovery. So I don't have too much time. Yeah. So the here is again using Sentinel-2 imagery. So you detect the fire is detected no longer, and we start the recovery mechanism here. Again, you have service specifications and tutorial to observe this, and it's a temporal window that's a variation that's analyzing the recovery of that vegetation. Then, for more, let's say, expert users, that not only have a dashboard with a pointer, red point, seeing that the vegetation evolving, they want afterwards to be able to execute services on demand, further analytics, further analysis on their data. So this, you have what we design in terms of Fire Desk workspaces. So you have a workspace where the user can, with the data processing services of Sentinel data that we package in a given way from the OEPCA that we had a presentation yesterday from Richard and so on. So we are packaging those algorithms in such a way that then they can become as services in this workspace. And this might be, okay, let's mix Sentinel-1 data, let's do change detection, let's do post-processing of that data. So we have a set of given services already defined that I was in that list, but then adding a new one is just a process. It's just something that you deploy. You deploy just a new type of capability into this workspace. Sorry. Now, what we are doing, we are currently now focusing on two main study areas. So we are focusing on use case. So this is this is in development. The Copernicus LAC is still in Europe. T-Systems will then be deployed in Panama when they have the capacity there. I hope by beginning of next year or mid of next year. And here we are training in few cases, like the example I gave you before, the Chile wildfires of 2023, and also a bigger area on simulating a more larger area of doing the monitoring of the near real time, so examining how it would be the near real time monitoring of bigger part of Central America from Guatemala to Colombia, and doing this type of analysis, and then discussing with the different stakeholders locally to see, okay, what types of further analysis do you want? What type of data, or even their own algorithms, their own applications, their own type of analytics they want to process. And here there is, so in fact we are free project. There is also another project from the Copernicus LAC that is really involving the stakeholders. And this is also in the EO Services project that INDRIS, we are talking with different stakeholders in different countries and trying to understand what are their potential use in terms of this type of, in this case, the wildfires, but then all the other thematic services that we are focused. And this is important, I think, is a very important point of the overall Copernicus LAC initiative. Not only this, is in the sense that it's not providing ready-made information for a given community, but trying to understand that with the Earth observation data that Europe provides, the services, the hosting, people are able to use the services or even to bring their own services where they do their own analytics, or they can sort of their local garage, local cluster, local computer, sort out their algorithm and deploy it into a platform. And now, really, I think it's the last slide. So the last word of the conference. In conclusion, so this is a good example. You see, the wildfire is a good example in terms of, because it covers the different areas. So we have different stakeholders that we can bring together here and see that, yes, we are doing that observation, we are number crunching, but then we'll need to have different windows, different ways of showing that information. And when you have such a vast number of stakeholders, some just want a PDF, some just want a graphic, no, another one wants to have the real data. So we need to be able to do this type of degrees of freedom of accessing that information. And then this also shows the way, in a sense, when we will have all the Copernicus LAC Center in Panama, the types of data, and the motivation for the region itself to bring their own algorithms and so start using Sentinel data in a much wider way. I'll leave you here with lots of links. Basically, this is a project, this part of so Copernicus LAC infrastructure is managed by Terra2. Copernicus LAC services is with Indra, and we are helping them also in some of the services. You have the platform itself already available. This is being deployed currently at the Copernicus Data Space Ecosystem in T-Systems. Then we'll need to be moved to Panama. But then you have also online documentation of what are the components of the platform, what are the open source components, how do you integrate them? So this is coming or from the open source world or from the Earth Observation Exploitation Platform Common Architecture part. And then you have also the services and documentation of how it works in terms of services. So you have all the links here. So I think it's all. Thank you very much. Thank you for your attention.
Thanks a lot. Questions from the audience? If not, I would like...
They want to go home.
Sorry. It's such an interesting topic, and I think that it goes also beyond what is happening now just with the LAC in Panama. But I was wondering specifically for the fire, and since you showed us the whole fire cycle, how do you see the cooperation or the integration of the private sector with companies like Aurora Tech, who are, providing a website with all kind of information similar and an own mission and so on?
So there are two facets here that are quite interesting. One thing is that, for instance, Indra Spain is a company, a big company in Spain. Their team now I think half of their team were in the research area doing the original algorithms that is then in the CCI and so on. And now they are doing it as more an evolution of that service. So this is a big thing in terms of, okay, yes, we did it in research, it was in ESA, but now it becomes a service that a private company is pushing and asking us to deploy it and to help them to optionalize. In terms of Aurora Tech, yes, we met them in Vienna, the LPS, and yes, we are talking with them and seeing the potential. I met, I don't remember his name, but we met and we are having discussions to see how we use their data, how this can be applied there. So it's a very good opportunity here to do it. Because the platform itself then in Panama, you have an open way of deploying new services. Beginning, we want to be the countries and the institutions, the local institutions, are able to deploy their own services in Sentinel data. But also companies in Europe or other open source projects, they could evolve and be included there.
Thank you. So thanks a lot for everyone. Thank you for these interesting topics. And I think it was really good to have this session at the end where we bring more in the services already and the applications of all these technological developments we discussed more in detail before this last session. And now I think we will have the closing. So thanks a lot for all the presenters of this session and for the audience.
Thank you.